Hello everyone, we're now going to start with section number 4. Bias does not mean imperfect. So far we have talked about bias, right? We have been able to calculate whether a system is biased or is not biased, but we must understand fundamentally that a system can have bias, and at the end of the day, the only thing that matters is, can I still use this system for what I need it for, okay? Remember that we measure mainly to determine whether a part is good or bad. We also measure for proper process optimization. We must always consider what bias means for our system and our existing implementation. So for this, we're going to look at one example. Imagine that we're creating a wooden furniture and we measure using a high precision CMM machine that is not properly calibrated. The results of measuring an 8-inch gauge block are shown below. So previously, we would have simply copied the information. If you look closely, you'll notice that none of the results are at 8 inches. Most of them are below 8 inches. So I would copy and paste my information into Minitab, stat basic one sample t-test, and then do a hypothesis test for an 8-inch gauge block. Now from here, I would look at my data, and I would determine that evidently, there is bias, and I can see that the bias is negative. I'm reporting the part as being smaller than it actually is. So far, I would close out my report and say the system is biased, and that's the same thing that we have here, right? Now the question is this bias significant? If I look at the data, I'm reporting parts as being around 0.01 inches smaller than they actually are. You might say that's significant, you might say that's not significant, but it depends on the implementation. So academically speaking, the bias is significant because our p-value is below 0.05 and it measures 0.01 units. Now please imagine that we're going to use this CMM machine to measure wooden parts that have tolerances of 3 inches plus minus 0.5 inches. Should we stop using the CMM machine because it's biased? If the part has a tolerance of 3 inches plus minus 0.5, the specifications are between 2.5 and 3.5 inches. At that point, having a system that is biased 0.01 isn't really that significant, okay? The fact that my system is biased toward reporting parts as being smaller than they are is not going to be the difference between accepting or rejecting a part. Parts will either be accepted because they're within spec or they'll be rejected because they're out of spec. But the bias is not going to cause people to start to second guess whether they should accept or reject the parts. Now, let's consider that the same part was not built at nominal and was manufactured at around 2.75 inches. Would my CMM machine negatively impact my output? No, because instead of saying that the real world part is 275, I would report it as 2.74, still well within spec, okay? So what this means in conclusion is that the impact of bias depends on our tolerance. If the tolerance is multiple times wider or bigger or greater than our bias, then there is no risk of miscategorizing good parts as bad parts and vice versa. Now we're going to look at a new example. Let's say that we had the same example. Okay, so we took our 8-inch gauge block and we got the following results. We're going to paste the information over into Minitab. We're going to do basic one sample t-test. And again, C3, which is our column that has our data, and our hypothesized mean of 8. If I look at my data, I can see that I have a p-value below 0.05. So same conclusion as before, bias exists, right? Now, if I look at my mean, I can see that it's at 7.60. Confidence intervals between 759 and 760. So I'm reporting parts as being 0.40 inches smaller than they actually are. So real world condition, the part can be at nominal 8, but I'm going to report it at 7.6. At this point, the bias is actually going to start to be significant. And we're going to demonstrate it with an example. So some people might say, well, my part is still within spec, right? I'm not going to be rejecting a part that measures 8 inches because I'm going to find it to be at 7.6. And yes, if the part is built at exactly 8 inches, then there will be no problem, right? But what happens in manufacturing is when quality reports that the parts are actually small. Let's say I get my report, right? And I know that I set up the machine at 8 inches, but the parts are coming out according to the quality system at 7.6. At this point, I would actually ask my team, hey, please adjust the machine to make bigger parts because they're too close to the lower spec. So manufacturing is going to go and adjust the machine, right? And during machine adjustment, let's say they can't get it exactly at nominal. So they were currently at 8 inches real world condition. They adjust machine parameters to make parts bigger. And during their adjustment, they reach real world conditions of 8.6. Since my machine reports it as being 0.4 inches smaller than it actually is, quality is going to tell me that I'm right in the money. I'm at 8.2 inches. Parts measure 8.2. But real world condition is that the part is actually 8.6 inches. So immediately when I release my lots over to assembly is not going to be able to assemble the parts because while quality says that it is 8.2 inches, real world condition is 8.6. Okay. So if we could set up a process to be exactly at nominal, then our bias maybe in this scenario wouldn't be that significant. The problem is that manufacturing adjusts the manufacturing process based on quality's feedback. So if quality says the parts are really big, quality says the parts are really small, manufacturing will adjust accordingly and we might not be in proper real world conditions. Okay. So in summary, as a general rule, bias will matter if it eats up 15% or more of the overall allowed tolerance. Please note that this rule is not a standard regulation. It is a general QE Academy recommendation based on professional experience. So, how do we do the calculation? Let's say that we have a system has a bias of 0.15 inches, which can be reporting samples as being bigger or smaller than they are. It doesn't really matter. The point is that the bias is exactly 0.15 inches. The tolerance of the parts that I want to measure are 5 inches plus minus 0.5 inches. We would now calculate accordingly. System bias divided by process tolerance. My bias is 0.15 inches. I will divide that by 0.50 inches, and this gives me 30%. If we keep this system in place without recalibrating, the bias by itself would eat up 30% of our allowed tolerance. This means that quality and manufacturing will adjust the process trying to get it into nominal and will run the risk of creating out of spec parts. Let's look at a new example of how to calculate. Another system has a bias of reporting parts 0.5 inches bigger than they are. The process tolerance is 10 inches plus minus 2 inches, so from 8 inches to 12 inches. We would calculate accordingly. My system bias, 0.50 inches, divided by 2, that gives me 0.25, which is 25%. Again, this bias is exceeding the recommendation of a maximum of 15% overall allowed tolerance. If we keep this system in place, a part made at nominal settings of 10 would be reported as 10.5. Quality and manufacturing would adjust the process to make the part smaller, and after adjusting, let's say I get 9.8 inches on the CMM. The real world condition of the part might be around 9.3 inches. In this scenario, the bias by itself is eating up 25% of my allowed tolerance, clearly not ideal. Now, you might say, well, but the parts are still within spec, right? Remember, this is just a variation that my measurement system is introducing into the system. We are never taking into account in this calculation the part-to-part normal variation. No machine is perfect. So machines, when they're manufacturing, they're going to make parts that are a little bit bigger, parts that are going to be a little bit smaller. So that is normal. There's always going to be some uncertainty when manufacturing. But we want our measurement results to be accurate to real-world conditions. Now, let's say that in this example tree, our final system has a bias of reporting parts 0.8 inches bigger than they are. The process tolerance is 500 inches plus minus 6 inches. So imagine, you might say, well, why would I have such big tolerance, right? Well, you might have a spool of thread, for example, or a spool of wool. So in those types of scenarios, high tolerances are common. Now you might say, well, is this acceptable or not? We have a deviation of 0.8 inches, which is actually quite high, divided by my tolerance of 6, and that gives me 13.33%. So in this scenario, I could keep this measurement system. The tolerance is big enough to accommodate such an extreme bias on my measurements. Now, please remember that these are general recommendations and not hard rules. If you decide to document these recommendations into your corporate MSA procedure, you must make sure to comply with the rule. Otherwise, a non-conformance may be raised by your auditor. In plain English terms, if you write this rule into your MSA validation corporate procedure and say bias cannot exceed 15%, then you're going to have to meet it because you yourself are saying, I will meet the spec. But if instead you simply keep this rule in mind and try and always be below 15%, and let's say one time you're at 18% or 19% and the team says, well, that's fine, and you do not meet that 15%, well, if it's not documented, this is not a hard rule. The FDA or ISO is not going to come in and say you're above 15% or below 15%. Okay? Your corporate procedure might even say, well, we want to be below 10% to be a little bit safer. Or you might say, well, this is wood manufacturing. We're not really worried about it, or spools of wool. So we're going to leave it up to 20% or 25%. Okay? Just try and keep it as low as possible. Ideally, bias will always be controlled with proper calibration.